Particles P and Q of masses 0.6 and 0.4 kg respectively are attached to the ends of a light inextensible string. Okay, I'm going to resolve the components of the weight on P. This would be mg sine theta. So this would be 6, mg would be 6 sine theta, and then this would be mg cos theta. So 6 cos theta. This would be R, the normal contact force, and this would be tension. There's no friction mentioned in the question. Otherwise, in the direction of T, there would be friction as well if the component is P was moving downwards. Okay. And then for Q, we'll have tension in this direction, weight component mg sine theta in this direction. So 4 sine theta and 4 cos theta in this direction, and R in this direction. And since P is heavier, it's going to move downwards, and Q is lighter, it's going to move upwards. Again, there's no friction mentioned in the entire question. If there were friction, there would be a frictional component here as well, or we would make a downward force of friction here as well. Okay, back to the question. The string passes over a smooth pulley, which is fixed at the top of a vertical cross section of a triangular prism. The base of the prism is fixed on a horizontal ground, and each of the sloping edges is smooth. Okay, they've mentioned smooth, so no friction. Each sloping side makes an angle theta with the ground, and sine theta is given 0.8. Okay, initially the particles are held at rest on the sloping edges with the string taut. The particles are released and move along the line of the greatest slope. Find the tension in the string and the acceleration of the particles while both are moving. Okay, again, P is moving downwards, so we're going to use Newton's second law on it. It's going to be forward force, which is 6 sine theta, minus backward force, which is T, is equals to mass, which is 0.6 times acceleration. So forward force minus backward force is equals to ma. This would be 6 times 0.8 minus T is equals to 0.6 a, which makes 4.8 minus T is equals to 0.6 a. This would be equation 1. Okay. Next, we will form the similar equation at Q. This was at P. Now at Q, forward force would be the upward force T minus downward force 4 sine theta. Sine theta is again 0.8. So T minus 4 sine theta is equals to mass times acceleration. Mass is 0.4. A has to be found. So T minus 3.2 is equals to 0.4a is the second equation. You solve equation 1 and equation 2 on your own, and you should be getting 3.84 newtons for the tension and 1.6 meters per second square for the acceleration, and part 1 is done. The speed of P when it reaches the ground is 2 meters per second. Okay, so when P reaches the ground, its speed is 2 meters per second. Okay, that means that as P reaches the ground, Q is going to move the same distance upwards. Okay, so as P reaches the ground here and its speed becomes 2, same will happen with Q. Q will move the same distance upwards and its speed will become 2. So let's say this would be 2 and its initial speed was 0. Okay, and we know the acceleration in this system, acceleration for both the particles is 1.6 meters per second square. Okay, similarly here, U is 0, V is 2, and acceleration is the same, 1.6. Okay. On reaching the ground, P comes to rest and remains at rest. Q continues to move up the slope, but does not reach the pulley. Find the time taken from the instant that the particles are released until Q reaches its greatest height above the ground. Okay, so we need the time for Q to reach its maximum height. Okay, we'll talk about maximum height in a bit. First, let's find the time that Q will take in this part. So we have V, we have A, we have U, we need T. So we can use V is equals to U plus AT. So 2 is equals to 0 plus 1.6 times T, which gives 1.25 seconds. Okay, so this time is 1.2 seconds. Okay, now as P hits the ground, the string becomes slack. So this string slacks, it slacks. Now, this particle Q does not stop instantly. It gets a forward push and it still travels upwards for a while till its final speed becomes 0. So now this V will be called U. This becomes U. Now we're talking about this part of the journey exclusively. So for this part of the journey, V is 0, U is 2, and we need the time for this part of the journey. But we're missing acceleration for this part of the journey. Okay. So for the acceleration, its value is going to change. It's not going to stay the same. Earlier we got an acceleration, which I've rubbed. What was it? It was I think 1.6. Yes. So it's not going to stay 1.6. That is because since the string has slacked, the forward force, which is the tension, is now 0. So we're going to reuse this formula, which I've also rubbed. And we're going to reuse the Newton's second law formula on Q and make the forward force 0 this time. So we need A now. So again, let's apply Newton's second law at Q. So at Q, forward force of T is now 0. Backward force is the same, mg sine theta. M is 0 0.4, g is 10, and sine theta is 0 0.8 equals to ma. So 0 0.4 times a. This gives us an acceleration of minus 8 meters per second square. So acceleration is minus 8. Now we can find t and then add it to this t. Okay, so we're going to use v is equals to u plus at again. So 0 is equals to 2 minus 8 times t. T comes out to be 4. Sorry, not 4, 1 over 4. And now, which is 0 0.25. Now we add both the times. 1.25 plus 0 0.25 gives 1.5 seconds, which is the final answer.